Okay, so first of all, welcome to Physics Colloquium. My name is Victor Galiskin, in case you don't know me. I'm professor here, and it's my pleasure to introduce another Victor Yakovenko, who's been here since '93. So Victor got his degree at Landau Institute in Moscow back in 1987, where he worked under Dzelashinsky, who was one of the founders of the modern condensed matter physics. So then Victor stayed at Landau for a while and moved to various visiting positions in Europe, in Cambridge, Orsay, France, and etc. And eventually moved to the US, first as a postdoc at Rutgers, and then, as I mentioned, as a faculty here at the University of Maryland. So Victor has done a lot of important work in quantum antibody physics, in particular one-dimensional systems. And in the early 2000s, he co-founded the now kind of booming field of economic physics with his milestone paper, Statistical Mechanics of Money. And it's a very interesting field that combines StatMech and, well, I guess, economics, etc. So, and today he'll be talking about yet another interdisciplinary subject, the mathematics of human population growth and CO2 emissions.
Okay, thank you very much for the introduction. Okay. So anyway, let's start. So basically the plan of the talk is that roughly consists of two parts. First part about human population growth, the main first part of the talk, and then the second part about CO2 emissions. I wish to quickly acknowledge my collaborators. So I have been doing this project for more than a year by now. It started with Ethan Levy, who was undergrad here. He started, did some preliminary work, but quickly dropped out. And then most of the work was done Andrew Dior from Ohio, as undergraduate student who contacted me on the internet looking for a project. And so he did major part, and then he dropped out because he was admitted to summer undergraduate program at Santa Fe Institute. Okay, so then I started working with Thomas Zhelezniak from Langley High School, high schooler, with some help of his father, Anatoly. For those who may remember, Anatoly was my first graduate student in Maryland when I arrived here 30 years ago. So anyway, let's move on. yes, it's the next generation. Yeah. Okay, fine. So let's start. Starting. When we kind of think about human population growth, okay, what kind of mathematical function comes to your mind to describe human population growth? Which function? Exponential. By far the most common answer is exponential growth. Sure. And I also thought so until one day. So I came to America in '91 as a postdoc at Rutgers University. And then about the same, I mean, in the fall semester of '91 and '92, I don't have a record exact, Sergei Kapitsa came to give physics colloquium at Rutgers University. I will show you some things about Kapitsa in a moment. And the subject of his talk was actually physics colloquium at Rutgers, was actually population growth. Okay, and he also published papers about this and so on. So quick notice, Kapitsa. So Sergei Kapitsa, he's a very well-known personality. He was a Soviet physicist who was very well-known because he was the host of popular science TV show. So it was like Mr. Science on Soviet TV. So absolutely everybody knew his name, etc. He is the son of Peter Kapitsa, who won Nobel Prize for discovery of superfluid helium. He was born in Cambridge, as you can see, and he was very well internationally connected. So anyway, let's go back. So Kapitsa comes to Rutgers, okay, and gives this colloquium about population growth. So what I learned from this colloquium, I was kind of shocked. So he says that population growth actually is not exponential in time. It is actually described by hyperbolic function of time. In other words, population n as a function of time is some constant divided Ts minus t, where t is time, and Ts is singularity time, where when t goes to Ts, it goes to infinity. Population goes to infinity, and the year for the singularity is 2026. Yes. And I hear, of course, this around 91. That's for the front. I said, okay, gee, I mean, I probably will be alive by that time. So I took a note. I took a back note at the back of my mind. And then I do the usual stuff, usual routine stuff. I finish my postdoc, I get faculty position here, I get my tenure and grants and all that stuff. But finally, last year, 23, I said, well, time is approaching. So I cannot postpone it anymore. If I don't do it now, it will be too late. So I dropped everything and started this project, okay? The project you will see in a moment. But for full fairness, it was not Kapitsa who actually proposed this. It was actually Heinz von Förster, who published in 1960, he and collaborators. He was in Urbana at electrical engineering. I'll show you things about him in a moment. So anyway, in 1960, he was published a paper in this Science magazine, and this is the title of the paper, Doomsday, Friday, 13th November, 2026. Now, this Friday, November 13th, this is a joke. That's his birthday, okay? but the year 26 is serious. That's a year obtained by fitting the data. I'll show data in a moment, okay? And this is the abstract of the talk. At this date, meaning 2026, population will approach infinity if it grows as it has grown in the last 2 millennia. So it was basically proposed in 1960. By the way, I was born in 1961. Okay, so what was the basis for this prediction by von Förster? Just a sec. Let me show von Förster before I proceed. Let me show von Förster. Okay, who is von Förster? Okay, so if he's von Förster, okay, Austrian scientist, physics and philosophy, okay, cybernetics. Just a sec. Well-known doomsday formula, but that's what I wanted to show. So polymath doing computer science, artificial intelligence, epistemiology, electronics, biophysics, memory, cognition, neural mathematics, cybernetics. That's kind, oh my God, that's kind of guy. Okay. So anyway, so he proposed this thing about this doomsday paper. Okay. So anyway, let's go back to the talk. Okay. So what was the basis of their claim? Well, this is the science paper has this graph. Okay. So basically what's shown is population in logarithmic scale, and this is time to singularity in logarithmic scale. This is log-log plot, and there are some data points, and there is a straight line. But I don't take this graph as anyhow convincing. So quality is poor. I mean, data, who knows what the data is, and quality of the graph is poor. So I don't find this graph convincing. But keep in mind, it was in 1960, so I mean, things were different those days. So anyway, I don't believe this graph, I don't take it by itself. But so what I wanted to do is this. I thought once the year is approaching, I wanted to take new, current data, the current data, and just reanalyze the data and check whether this claim was, anyhow appropriate or not. So that was a project. Get new data, do data analysis, and see what's going on, okay? So this is the project. So this is the first graph. It will be several, 6 graphs more precisely, and they're very busy graphs. I walk you slowly from this data, slowly. First of all, what is a data source? So, everything now is available on the internet, so we found this website, Our World in Data, and that's where we got the data. Okay, so let me show just for clarification what are the data sources. This is this website, and they have different data. This is basically an aggregator site. It's not their own data. They aggregate data from different sources. So specifically from I have to switch, from 10,000 years BCE, to whatever, 1800, that data was there from this database, whatever, in Netherlands. It's some Netherlands database in this time range. From 1800 to 1950s, Gapminder, the Swedish kind of data company. And then it was from United Nations. Okay. So it's stitched from several different sources. How exactly they do it, I don't know. It's, I just take the data as is. With one kind of clarification, instead of United Nations data for the most recent time, we actually use World Bank data. So this is from World Bank. Okay, World Bank, okay, they have their own data, which is somewhat slightly different from United Nations. This is from 1960 to the present time, then 2023. This is much simpler data set. The advantage is they update data, they have annual updates, they update every year. United Nations update every 2 years. So we decided to use this data. And by the way, if you look at this, the most recent data point is here. You see 8.02 billion, that's for 2023. Okay, strangely enough, United Nations says it's 8.2. Not 8.02, but 8.2. There is some difference. I don't know why. But long story short, we use World Bank data, okay? Because you might see those numbers in newspapers. So anyway, that's so much about the data sources. Okay, so now let's, yes?
So when it goes like 10,000 years back, the data is like from the census 10,000 years ago?
So anyway, the data we found starts from 10,000 BCE, and I just take the data as is. Like a series, experimentalists measure data points, I take experimentally measured data points, try to fit them. How they measure them, etc. in the laboratory, I don't have full control over this, I don't know exactly. I take data as is and try to fit them, okay? So data is available from 10,000 years BCE to 2023. So this is time, and this is population in logarithmic scale. And you see from here to here, it increased by 3 orders of magnitude, okay? So let's make the main panel. What you see here in this range, from 10,000 years to about, 4,000 in this range, you see it's pretty much straight line in log linear scale. Of course, we know straight line in log linear scale means exponential growth. So indeed, 10,000 years ago, the growth was exponential, okay? With a characteristic, so, this basically is usually associated with the name of Malthus. So the growth rate is, birth rate minus death rate, and you can, if you assume this to be constant, then of course you get exponential solution, and it's characterized by characteristic growth time t, which is actually about 3,000 years. So population was growing exponentially with a characteristic time about 3,000 years. Again, very quickly about Malthus. Of course, I'm sure you heard his name, but what is Malthus? Malthus, was British political philosopher, and in the late 18th century, he published about population growth. Okay, so growth was exponential, okay, in this time range. But then you see what happens. So as usual convention, the black points are data, and colored lines, these are fits to various functions. So this is fit to exponential function. But then you see data points go up. They go above straight line. So it means population growth becomes super exponential. It grows faster than exponential. So how can we fit that? First, I show you quickly something that does not work, and then I show you what does work. So there is a very well-known modification of this exponential equation. It's called Verhulst equation. I'll show you in a moment. And basically the idea of Verhulst, okay, so who was Verhulst? He was a Belgian mathematician in the 19th century, okay, and he wrote this equation, so-called logistic equation, which is, there are zillions papers in the literature. That was 19th century. You see this 19th century. So there are zillions of papers in the literature about this Verhulst equation. And so his logic was the following, that of course, as population grows, it exhausts resources. By exhausting resources, population growth slows down. So he added nonlinear term with negative sign. And so you see as population increases, the growth slows down, and eventually saturates, comes to 0. When these terms balance out, population growth stops. The solution of this is known as logistic equation. There are zillions of papers in the literature about this. However, importantly, it does not apply to human population growth, because this predicts sub-exponential growth, whereas what we observe is super exponential growth. So things simply doesn't work. Okay, so any suggestions how to modify it to make it work? Okay, time passed. Flip the sign. Okay, so instead of negative sign, let's put positive sign. Just flip the sign. Okay, so then you get this equation. Okay, and solution of this, it's easy to solve this equation, and interestingly, the solution of this equation as a function of time looks exactly the same as Bose function in statistical physics. Bose function, of course, is a function of energy, where this is a function of time, but mathematically they're exactly the same. By the way, this corresponds to Fermi function, by the way. So for the lack of better terminology, I call it Bose function. Because I found only 3 papers in the literature, as opposed to zillions of papers here, that actually discuss this kind of equation and this kind of solution. It first appeared in this paper by Joel Cohen in Science Magazine '95, exactly in the context of demographics, population growth, but it appears like in footnote, and it's not actually even compared with the data. So that's what we did. We took this function, Bose function, and tried to fit the data, and the fit works very well. So this blue line is the fit of the population data using this super exponential Bose function. The fit works pretty well, as you can see, okay, the blue line, until this point. This corresponds to about 1700. Around 1700, so this is zoom in. This is, this is zoom in from 1400 to 2023. Around 1700, population growth suddenly accelerates. Okay, suddenly accelerates. I don't know why, I will discuss it later, a bit later in talk, but the empirical fact is, around this year, 1700, population growth suddenly accelerates and becomes much faster. So this is, and this is the fit, red line is a fit, and red line is essentially the fit to essentially, roughly speaking, to this hyperbolic function proposed to von Förster. So next slide will show this in detail, but bottom line is, after 1700, population growth started, accelerated suddenly, and we are going to fit it with hyperbolic function proposed by von Förster. Just keep in mind, this Bose function, this equation actually interpolates smoothly between exponential and hyperbolic, because if you neglect nonlinear term, this gives you exponential, it gives exponential asymptotic. On the other hand, the population is big, you neglect nonlinear term, you get this nonlinear equation, and that gives you hyperbolic solution with a finite time singularity. By the way, the original Bose fit would have, when the denominator goes to 0, well, population goes to infinity. For the original Bose fit, that was around year 3000, far in the future. But then the growth accelerated and something, and that's what we have now. So anyway, next slide. I will basically neglect this term and just keep this term and discuss hyperbolic solution in more detail, okay? So we take this equation with linear term neglected just for simplicity. This nonlinear equation, of course, very easy to solve. You simply write it as derivative of inverse n, it's a constant, and of course solution inverse population changes linearly in time, correspondingly population itself has a singularity, okay? Now, if we consider this kind of hypothesis, then it makes sense to make a graph, not of population, because population goes kind of to infinity, but of inverse population. And inverse population is expected to be a linear function of time, okay? And this is the graph. So this is the graph of inverse population as a function of time in this range from 1400 to present time. This is the previous, Bose group, Bose fit. And this is the new data, data from 1700. And this is red line is essentially a fit essentially to a hyperbolic function. More precisely, it's not exactly a straight line. It's because it has a small Bose correction. But in the first approximation, it's really a straight line. So these are the data points, black points, and this is the fit. And if you extrapolate that fit, that inverse population is extrapolated to 0 in year 2030. So 2030. Okay, so essentially the prediction by von Förster was essentially correct. Well, 26, 30 is about, not a big difference. But yes, there is hyperbolic growth, and it does extrapolate to infinity in some very near future, okay? So von Förster is vindicated in a way, okay? So far, so good, or maybe not so good, okay? However, now next step. Of course, population cannot be literally infinite. It's just extrapolate a singularity, Whenever you have any singularity, it will be cut off. Okay, there will be, at some point, there will be truncation, it will be cut off, okay? And that's what we actually see in the data. For the last 30 years, after 2000, these are the data points. You see the data points here, they veer off, they deviate from this straight line fit. So this is the fit, but in the last 30 years or so, after 2000, the data point starts to deviate, okay? From this. So in other words, singularity will be cut off. And it will not happen, literal singularity, literal infinity. So how to do this? What mathematical function to use to describe this deviation from the singularity? And here is another mathematical proposition. See, if you look at this function, mathematically speaking, what is the problem with this? This time, this difference, t minus ts, it decreases, and reaches 0, then it changes sign. If you literally take this function, it will change sign after singularity. Population become negative. It doesn't make any sense, right? So in other words, physically, by all means, we have to prevent this function from crossing 0. In other words, what we need to have is avoided crossing. We need to avoid crossing 0. And this, of course, is a very well-known concept for those who do quantum mechanics. There is even Wikipedia articles called, I'm sorry, okay, avoided crossing, okay, avoided crossing, okay? So, this picture of level repulsion, I think I see this in every single JQI talk, every single JQI talk shows this level repulsion. For I don't know how many years JQI, for all those years JQI exists, and it's so point is, usual story, you get matrix element that produces level repulsion and prevents, energy level to cross, okay? So let's use this idea to do this modification. So here's a proposed modification. Proposed regularization, okay? So basically take this function, so t minus ts, we square it and add tau squared, some time tau squared, and then take square root, okay? Now this function is well behaved, it's regular, so it's always positive, it never crosses 0, okay? And if you take the inverse, that means the population itself is a square root of Lorentzian function. So this will be Lorentzian, and this is square root of Lorentzian. So basically, we essentially try to fit the data using this, what we call square root of Lorentzian function, and indeed we get a very good fit. So this is inverse population. We take this. The green line shows fit, which is very good fit. And instead of singularity in year 2000, what we get a minimum. okay, or corresponding when we get a peak. So in other words, instead of population going to infinity, we're going to get a peak and then decrease of population. So the singularity discussed by von Förster actually, because of regularization, becomes a peak. Well, for inverse population, it means a minimum, okay? And if you want to, this is for 300 years from 1700, but if you want to look at the recent data, say from 2015, okay, you know, any function near the minimum can be fitted by parabola. So this is the data point, we fit to parabola, and we find that the minimum is expected in 2030. The minimum of 1 over n corresponding to the maximum of population n itself, okay? So, okay, so now a few more things about this. Another way of obtaining this function, if you didn't like, you know, avoided crossing, there is another way of doing this. What is the problem with this function? The problem is it has a pole, mathematically speaking, it has a pole on the real axis, okay? Pole on the real axis is a problem, and we encounter this often in physics. So if you see, theorists, you know, when we see a pole on the real axis, what do we do in physics? We shift it to a complex plane, okay? We simply shift this pole to a complex plane. So in other words, we need to consider this variable as a complex variable, and then this, you know, position of the pole acquires some, may acquire some, you know, imaginary part, then pole is shifted to the complex plane, and there is no problem on the real axis. However, that's complex function, population of course is real, but you know, complex function you can write as amplitude and phase, and so if you identify the amplitude of this complex function with population, that gives exactly the square root of Lorentzian, gets exactly this fit, okay? You may ask what is the meaning of phase. I will show you toward the end of the talk, the physical meaning of phase, okay? So far, so good, right? Now, let me show just very quickly one slide in physics. This was population, but what inspired me? Well, what inspired me being a physicist, second order phase transition. So this is a paper, you know, PRL. This is PRL about organic conductors. Of course, I did my first part of my career doing organic conductors, and Sergei Brazovsky was my PhD supervisor, and I worked on these materials and these experimentalists who did measurements. So this materials has all kinds of phase transitions, including ferroelectric transition, which is second order phase transition. So what happens near ferroelectric transition? You know, the electric permittivity, you know, diverges because lattice becomes unstable, atoms spontaneously displace, and that's manifested as, if you measure response function, that's permittivity, it diverges as function temperature minus transition temperature, okay? But if you want to make a graph, this is second order, you know, Landau theory, but if you want to make a graph, it's better make a graph of inverse. You know, instead of this going to infinity, you take the inverse, that goes to zero linearly. This is the experimental measurements on these materials. This is inverse susceptibility or inverse permittivity as a function of temperature, 3 different materials. And you see it beautifully goes down to 0, that means to infinity, and then goes up again. The slope is a difference, you know, slope has factor of 2 difference because according to the Landau theory. So that's basically how second order phase transition looks in the inverse response function. So this material is really good. This material is not as good, so I mean, this little bit has roughness, you know, disorder. So this curve doesn't go all the way to 0, get rounded. You see, this get rounded. And this is even worse quality, rounded even more. So that's what you see in physics. You kind of approach a singularity, but they get rounded, etc. And basically what you have seen in population data looks, at least visually, very similar. So anyway, that was a small deviation to physics, but let's go back to population. So now we plot population itself, not the inverse population. So there is, okay, so basically red line is this hyperbolic singularity, which doesn't happen because get truncated. And the year of peak is 2030, then population of peak 8.2 billion, and the width of this transition tau is 32 years. It comes from the fit. Now, interestingly, you see, unless you come within 30 years of this peak, you will not be able to see it. So in other words, only after year 2000, there are signatures of this rounding off of peaking. Okay, now, and what is shown in this inset, okay, is basically the check how good is this fit, okay? So one standard way of checking this is essentially make a parametric graph. So this is, so for every year, we make a graph where the horizontal coordinate is the actual population. So for example, say 1980. This is actual population in this year, the empirical data. And here is theoretical expectation for this year. So in other words, this theoretical function. In other words, on one axis you have a theoretical function, on another axis you have empirical data. If there is a good agreement, this would fall on a straight line, okay? And indeed, data points pretty much fall on a straight line. Which, of course, there are deviation fluctuations, you know, nothing is perfect, but, you know, overall it's pretty good fit. Pretty good agreement between theory and experiment, and this goes on for 300 years, from 1700 up to present time. Single fit by single function fits in all things. Before 1700, of course, story was different, I told you before. Okay, fine. So 2 more slides about population, and then I will switch to CO2. Okay, so one question you may ask, why 32 years? So what determines the width of the transition? Why it happens at about 30 years, okay? And here is some story about transition from adiabatic to anti-adiabatic regime. Okay, so let's take logarithmic derivative of population, and that by definition is called growth rate, okay? And the inverse of growth rate is called growth time. It's just definition. So if growth is exponential, then you can easily see that the growth time is simply the parameter t in the exponential function, and it was 3,000 years, a long time ago, as I told you, okay? So 10,000 years ago, the characteristic growth time was 3,000 years, and that is much longer than human lifetime. That means during individual lifetime, almost nothing changed. Like, ancient Egypt, 1,000 years, one dynasty, another 1,000 years, another dynasty, etc. So the evolution was adiabatic, okay, on a human life scale. Okay, but now hyperbolic regime is completely different, because hyperbolic regime is scale-free. So if you calculate this logarithmic derivative for hyperbolic function, you'll find that the growth rate itself approaches singularity. In other words, growth rate becoming faster and faster. Correspondingly, the growth time, which is the inverse, is getting shorter and shorter. So for hyperbolic growth, you see, 300 years ago, the characteristic growth time was 300 years. 200 years ago, it was 200 years. 100 years ago, the growth time was 100 years. And now it's shrinking to like almost nothing. So the growth rate, the growth time is shrinking, and the growth rate is accelerating to totally crazy numbers. And the point is, it corresponds to anti-adiabatic regime. So this growth time is becoming shorter. The macroscopic growth time is getting shorter than individual lifetime. Okay, it's never been time like this in human history. So now is totally unprecedented time, like it never in human history. However, this is just for pure hyperbolic, which get truncated. So if you use avoided crossing, the truncated, then you can go through the algebra and you find that in fact this growth time is not shrinking to 0, but it has a minimal. It has minimal value, it has a minimum, which is actually 2 tau, simple algebra 2 tau, okay, and tau is 32 years, so 2 tau is 64 years, okay, and so that's comparable, that's more or less human lifetime, okay. So in other words, that I think explains why truncation happened at this time scale. Essentially you have, it's like in hydrodynamics, you have macroscopic scaling, or with, and then you basically time scale shrinks, until it reaches microscopic cutoff, which is what? Individual human lifetime. So in other words, this crazy hyperbolic growth kind of get truncated because it cannot accelerate anymore. It's already like time is equal to a human lifetime. So anyway, long story short, that the growth time over the course of human history has decreased by 2 orders of magnitude, from 3,000 years to about 32 years, and from basically adiabatic to anti-adiabatic regime now. Okay, so far so good. But now you might ask, okay, fine. What is official point of view on this? Okay, that's my presentation, that's my data analysis, right? But what do people say about this? So let me show you, official opinions about this. United Nations, of course, the population division. Oh yes, go ahead.
Sorry.
Yes. Mm-hmm.
What happens actually
After the peak.
Yes.
So after the peak, there will be decline of population.
No, but then after what happens?
I mean, after decline?
Yes.
Or whether it goes like to 0 or non-zero or something? Yeah, very good question. So if you literally take this Lorentzian function, well, if you take it literally, mathematically, it will go to 0. Okay? So that would say that the population will get extinct. But the problem is we cannot really predict what happens past singularity. You see, using present data, we can fit what's going up and in the near future when it starts going down. But we cannot predict what happens in the long future because things get scrambled. In other words, present data are insufficient to make very long-term predictions. We can only do short-term predictions, maybe like, let's say within 21st century maybe. But we cannot, cross singularity, you see, and know what happens far beyond singularity. It's just impossible.
But if you had a model that would explain
Yeah.
why you are getting, why the curves are falling,
Yeah.
then
Yeah.
you have a model.
Yes, but the problem, understand, but the problem is the following, that it may very well be that population will stabilize, okay? But according to this fit, it will stabilize at a level which is much lower than the peak level, okay? And the problem is there's not enough accuracy in the present data to determine that small value. It's like, WKB analytical continuation, You can determine big term, but you cannot determine small term. See, we go around singularity in complex plane effectively, right? So we cannot determine small correction. It's beyond the accuracy. It's beyond the accuracy. So in that sense, I cannot predict long-term future. I can only predict near-term future, yeah.
Following up on Sandra's question, so I think maybe the right question to ask is, what is the microscopic model that gives you this hyperbolic law in the first place before you regularize it? I mean, there are a million ways to regularize it. I don't know why you chosen this and not infinitely many other possible. Like, does anybody know why it was actually hyperbolic for?
Well, okay, so at the end of the last slide, I will show some equations, some differential equations. See, I first show empirical data because I want to get facts first. On the very last slide, I show some differential equations, more precisely 2 differential equations that do produce hyperbolic and this Bose, etc. So I will show you some differential equations that produce singularity. But to cut off singularity, that's more challenging, and there's no full answer at this point.
It's trivial, correct? Differential equation gives me a hyperboloid. And the question is, why does it exist in the first place? Is there a microscopic model?
Okay, right. Okay, so let me put it this way. This is a colloquium. So by definition, colloquium is supposed to stay at trivial level, right? Okay, and anything beyond trivial level, that has to be specialized discussion among, yes, right. Okay, so point is, I only scratch the surface. Keep in mind, I only scratch the surface. And for the most part, I just present empirical data, okay? And a little bit of trivial, equations at the end, but not full. So I don't have full kind of theoretical and mathematical description. Okay, let's put it this way. A story about Kepler. Okay, there was Tycho Brahe, who collected lots of data points, reams of data, okay? Just, gigabytes of data written on paper, okay? And he's a postdoc. His name was Kepler. And Kepler stared at this data and somehow occurred to me, well, how about they fit them to ellipses? And he fitted to ellipses and it worked. It worked great. And so he reduced the reams of data points to only a few parameters for ellipses, okay? So he produced called compression of information. Instead of all these data points, you only need to know a few parameters for ellipses. That was contribution of Kepler, okay? No idea why, but it worked, okay? And then later came Newton and said, oh, we know the ellipses. Why the ellipses? Well, he wrote his law. So you see, it requires 3 steps. Collecting raw data, fitting data to simple mathematical functions, and then trying to explain, if you're lucky, with some deeper mathematics. I'm at the second stage, fitting data with simple functions. I'm not in the third stage of Newton. I'm a state of Kepler, not a state of Newton. But you're welcome, to work on, to continue. So anyway, okay.
Do you have any, a more specific question?
Yeah.
What happened in 1700?
Next slide. Next slide. But let me finish with this slide. Let me tell you what United Nations say about this, right? Okay, so United Nations, they have, of course, specialized division about this. So they publish their reports every 2 years. So the latest report in 2024, okay, and in this report, this is July this year, published July this year, and they admitted, as far as I know, for the first time in those reports, United Nations officially admitted that there will be a peak of population peak. This is the first line in the report, first item in the report. There will be population peak and then subsequent decrease of population. Until this year, they actually avoided the subject. Although it was discussed for a long time, they were kind of, but now they admitted there will be peak and there will be decrease. Now it is official. The only question is when. So they say, well, it will be like around 2080, according to so-called medium scenarios. Okay, fine. But what was in the previous report, 2022? This is a graph on their report. And this is the models. Victor, you asked about models. Here are results of calculations of the models of professionals who spend, who do this for a living. Okay, so what they say? Their models, fertility, growth rate, all that. So what's prediction? Well, population may go up and keep going up. It's called high scenario. Or it may kind of saturate, it's called medium scenario. Or it may go down, it's called low scenario, or anywhere in between. Pick whatever you like, okay? So this is like in weather forecast. There is a cone. And so their prediction, what's going to happen to the population? Well, anything, okay? So much for predictions. Okay, but however, if I look at this and take the low, as you can see, if I take the low scenario, well, that has a peak around 2050. Okay, not too bad. And I propose in 2030, right? So bottom line, we will see. It's not too long time to wait. Who is coordinator? Please schedule me next colloquium in 2030. to report an update on this. However, as we were writing the paper, so Vicky, I'm making my bet. The peak will be 2030, and we'll see. Okay, but as I was writing this paper, this article appeared in Wall Street Journal by Greg Gibb, a well-known journalist, it's suddenly not enough babies, and this is the opening paragraph. The world is at a starting demographic milestone. Sometimes soon, the global fertility rate will drop below the point needed to keep population constant. It may have already happened, okay? So, and there was interviews with various demographers, and they basically say that those young forecasts, they get shifted to close, the peak gets shifted, from one report to another, it gets shifted closer to present time. So point is, in the view of this, I think, peak at 2030 is not entirely crazy, but we will see in 6 years, okay? Please come. Okay, so that's all about population growth. Next, I will switch about, what happened in 1700 and about CO2 story, okay? So let's move on. Okay, great. So what was special about 1700? Well, of course, Industrial Revolution happened around this time, and the Industrial Revolution was about extraction of fossil fuels. You know that, right? So in fact, the first version of the paper, submitted version of this paper, we wrote some kind of hand-wavingly, like, 1700, the acceleration of growth is probably due to Industrial Revolution, fossil fuels, And the referee said, this is like hand-waving argument. There's no data, there's no kind of, justification, just blah, blah, blah. So we said, okay, fine. So let's look at the data. Data on CO2 are available. Okay, this atmospheric data is available. So I asked students to get those data. And so that's what students produced. Again, this is a busy graph. I will walk you slowly through this. So first of all, let's focus on the main panel. So this is, again, from about 9,000 years BC to present time. So the open blue circles, this is CO2. This is atmospheric level of CO2 in ppms, okay? And what you see is some background and then explosive growth of CO2. This is a famous hockey stick curve, right? There is some base, and then there is a explosion, okay? This is very well-known hockey stick curve for CO2, okay? What are the black points? The black points is actually population in linear scale. So on this scale, linear scale, population was basically close to zero, and then exploded at about the same time by about the same magnitude. So you see, both population and CO2 exploded at about the same time. But it's not very well visible on the big scale, so let's look at the inset. This is zoom in from 1700 to present time. So this green line is population I showed you before, and this is that fit that I showed you before, the green line is population. These open blue circles, this is CO2 level, okay? CO2 level in atmosphere, and as you can see, the growth of CO2 is pretty much parallel, pretty much the same as growth of population. So they basically grow hand in hand, like in parallel, okay? So we see quantitatively that the growth of CO2 essentially follows the same pattern as growth of population. However, again, this is kind of approximate picture. Let's do it more exact. Let's do it more quantitative, more exact. This is a parametric graph. So again, for every year, we make a graph where on horizontal axis we plot, for example, this year, the CO2 level in this year, and here population of this year. So it's a parametric graph of population versus CO2 level as a function of time. And what you see is from 1700 to 2000, essentially it follows straight line, essentially falls on a straight line. So for 300 years, there is essentially linear relation between CO2 level and population level. Okay, so they basically grow hand in hand, kind of, they're linearly related. Okay, and I will exploit this, and I will discuss this in some more detail. But before we proceed further, I just wanted to point out some kind of striking facts. For example, if you look at the increase of CO2 since, for example, 1700, that's the CO2 in 1700, to present time 2023, okay, so this is the increase of CO2 in 300 years. Let's divide it in half, so first half and second half, okay? And which year corresponds to half and half division? This year is actually 1987. So in other words, as much CO2 was emitted after 87 as during the previous 300 years of human history, okay? And by the way, incidentally, 1987 is the year of my PhD, okay? So my PhD is the milestone of human civilization. So as much CO2 was emitted after my PhD during my academic career as it was emitted in the previous 300 years before, just to put things in perspective, okay? But anyway, so as I said, there is linear relation between CO2 and population for 300 years. However, as you can see, after 2000, this curve starts to deviate down. So there is deviation, systematic deviation after year 2000. The curve deviates down. Why is that? Well, the reason is the following. If you look at this graph, you see population, as I said, is preparing to peak. right? Growth of population is slowing down because, as I said, it's gonna peak, pretty soon. So, and then will decrease, okay? On the other hand, CO2 level cannot decrease, okay? At least not on this time scale. Because whatever CO2 is emitted in the atmosphere stays for a long time, like 700 years or something. So whatever is emitted just stays in the atmosphere. It cannot decrease on this time scale. So that means CO2 as a function of time must be monotonously increasing function of time. It cannot have a peak and decrease, okay? So initially they follow the same pattern, but then they start to deviate. And by the way, the pattern, because the fact that we have linear relation, it indicates that CO2 growth also follows hyperbolic pattern. Because, population grows hyperbolic pattern, as explained. I mean, CO2 also grows hyperbolic pattern for 300 years, okay? So now there is a question, there is a mathematical question. Can we fit the CO2 data by some kind of, simple mathematical function? This mathematical function has satisfied, say, the following conditions. First of all, it has to have hyperbolic asymptotic in the past, okay, because population does. Second is, it has to be monotonously increasing function, okay? And third is, let's make optimistic assumption that CO2 level will eventually saturate at some level. So it has some maximum level to saturate. It doesn't have to be, but well, let's make this optimistic assumption. So anyway, a function that is monotonously increasing, saturating, has hyperbolic asymptotic. Well, in case you don't know, arcotangent. Arcotangent is a mathematical function that satisfies these conditions. So arcotangent increases, has inflection point, and then saturation. And by the way, why arcotangent? Because in fact, Kapitsa, remember I showed Kapitsa on the first slide, Kapitsa proposed arcotangent to describe population growth, okay? Because Kapitsa, he did it in the early 90s, and he couldn't, imagine there would be decrease of population, so he assumed population would increase and then saturate. So he proposed arcotangent for population fit. Now, it turns out this fit does not work for population, okay, we checked it. However, interestingly, this fit arcotangent works very well for CO2. So this red line is a fit of CO2 level by arcotangent, okay? And so what are the characteristic features of this? It has, this year 2030, where population has maximum peak, CO2 has inflection point. That means before this, second derivative is positive, and then second derivative becomes negative. In other words, okay, so what does that mean? It makes sense, let's consider annual emissions. Let's take time derivative, CO2 over time, and this is shown here. This is a time derivative of this function, and these are basically annual CO2 emissions, okay? And by the way, derivative of arcotangent is actually Lorentzian, so this is actually Lorentzian function, and so according to this fit, CO2 emissions so far, they are increasing every year. So every year, we emit more CO2 than we emitted previous year, okay? However, our prediction is that by 2030, annual emissions will reach peak, and after 2030, annual emissions will start to decrease. Of course, CO2 level will continue to increase, but annual emissions will start to decrease after 2030, and at the usual half width, half height and half width, they will drop by a factor of 2. They're determined by the width of the Lorentzian, and the width of the Lorentzian, according to fit, is actually 40 years. So in 40 years after 2030, that is by 2070, the annual emissions is, according to my prediction, are expected to drop by a factor of 2. Yes, sure. Say what?
Are you trying to get a prediction
Yes.
for the red car based on what the population is doing?
Okay. So yes, that's a good question. The answer is yes and no. Okay. So you see, this game can be played different ways. So one way to play this game is to say, well, we do separate fit for population, we do separate fit for CO2. Okay. Just and so it happens to be that for population it is square root of Lorentzian, and for CO2 it happens to be arcotangent. Okay. So one can try to do just separate fits, okay, depending to which audience you are trying to talk. Now, more ambitious goal would be, can we actually connect them, okay, and get them from the same framework, get both things from the same framework, okay? And next slide I will show you some attempt to get them from the same framework, single framework, but it doesn't work perfectly, as you see in a moment. It sort of works, but not quite perfectly. So, at a simple level, one can say this is a separate fit. But the next level, I can try to combine them, but there are certain difficulties, okay? So let me show next slide, okay? so you may ask, how good is this arc? Let's see, what anything else I wanted to say about it? I think I said everything I wanted to say. Okay, so one can ask, how good is this arc-cotangent fit? Because that graph, is a small scale, etc. So what we show here is, again, parametric graph for each year. On the vertical axis, we show the actual CO2 level, the actual data for CO2 level ppm, and the horizontal axis, this is theoretical function arc-cotangent. So we plot data versus arc-cotangent, and if there is agreement, if this is a good fit of the data, we are supposed to get straight line, and we do get a straight line. From 1700 up to present day, for 300 years, the data fall in a straight line. Now, I should say that this function, arc-cotangent, has two adjustable parameters. One is the singularity time, TS, which we don't fit. We simply take it 2030. We take it to be the same as population. We take it. But then adjustable parameter is tau f, the width of this transition. And that's where we do fitting. If you don't select it properly, you don't get a straight line. So we optimize, and the optimal value is 40 years. So if tau is selected to be 40 years, that's where point basically falls in a straight line. And then, of course, you read off the slope and the offset and gives you full data fit. So bottom line is, this will be the baseline, kind of the baseline, and CO2 level above the baseline, the increase of CO2 above baseline follows arc-cotangent with these parameters, okay? I'll show one thing about population in a moment, okay? But so we have predictions. We have predictions. What will be CO2 level at all those years? 30, 70, etc. Okay. This is of course this is the singularity time or former singularity time. This is the width plus minus tau f, the width of transition period, and this is minus infinity. This plus infinity time. Okay. Now, but CO2 numbers may be not so informative. More informative would be degrees of Celsius. Okay. So we can translate actually ppm into Celsius. There is a well-known empirical relation. I mean, this is widely discussed in the literature that 100 ppm approximately corresponds to 1 degree of Celsius. So we take our ppms and convert them to Celsius, and this is the increase of temperature in Celsius relative to baseline. This is our baseline, which is not exactly the same as other organizations do, but approximately the same. So the increase from baseline to the middle, this is like TS 2030 is like middle of transition. There is equal increase from baseline to the middle of transition and from the middle to the ultimate saturation. So this increase 1.8 degrees Celsius, okay? And that roughly corresponds to this 1.5 degrees Celsius that all these organizations are talking about, where we're supposed to stop it. And as you look at this graph, there's absolutely no way, looking at the data trend, to stop it at 1.5 degrees, which already either has been achieved or is being achieved. So that by 1.5 essentially has already happened. Okay, so temperature will continue increase. But according to this fit, by 2070, 40 years later, it would increase to about, 2.7 degrees Celsius. Okay, that's where hopefully CO2 annual emissions drop by a factor of 2. Okay, fine. Anyway, so this is just the data. And by the way, this graph, you see, there is absolutely nothing but population. On this slide, there's nothing but population. It's pure atmospheric science. Fit of ppm, fit of temperature, no single word about population. Why it is good? Because I can take this slide and give it to atmospheric science department if they don't want to hear about population. And many people don't want to hear about population. Just take this slide and fit your atmospheric data with it, okay? However, if you do want to make connections with population, okay, here is a possible answer. Here is a possible answer. Remember this complex function with the pole in the complex plane, right? It has amplitude and phase, and simple mathematical exercise, remember the amplitude is square root of Lorentzian, the absolute value of this, but what is the phase? The phase is actually arc-cotangent. So the phase, the complex phase, the phase of this complex function is actually arc-cotangent. So it looks like, well, optimistic, well, not, it looks like it may be possible to fit both population and CO2 using single complex function, okay? It works beautifully, however, not quite. There is some little problem. Little problem is that the tau is supposed to be the same for both, okay? But from our data fits, we find that the tau for CO2 happened to be 40 years, whereas tau for population happened to be 32 years. So even though this is Lorentzian and this is arc-cotangent, they have slightly different fitting parameters. And that spoils the beautiful mathematics, okay? Unfortunately, for me, as a theorist. However, the difference is not so big. It's only like 20% difference. So, one can say at approximate level it might work, okay? But that's as best as I can say, okay? But anyway, so I'm getting to the last slide of my talk, which is differential equations. Okay, so this is the data. And finally, I show you differential equations, and then we can discuss. Okay, so those, let me show you two trivial, I emphasize trivial, coupled differential equations to describe this thing. Okay, so let me first introduce some somewhat abstract variable f. So what is this variable f? This variable f represents so-called vaguely defined achievements of human civilization, which allow humans to outcompete the rest of biospheres. Humans, as you know, effectively outcompeted the rest of biosphere. Okay, and I want to characterize by some abstract variable f. But what is manifestation? You see, in biology, the population growth is the signature of success of biological species, okay? So success of the biological manifestation of success of humans is the growth of human population. So essentially I take population growth, I write population rate of growth as this variable f with some normalizing coefficient. So long story short, I propose two simple differential equations. So I say the human population, time derivative of human population is human population times rate of growth rate. And growth rate I express in terms of this strange variable f. It's just so far simple, trivial rewriting. So population growth proportional to population and proportional to this variable f, the achievements of human civilization. However, these achievements themselves also have differential equation. For example, you might think of this f, for example, as knowledge, technology, science, that kind of stuff. Okay, so the growth of knowledge is proportional to already obtained knowledge, right? And proportional to number of people who are involved in producing this knowledge, right? So it's a product of number of people involved and achievements already made, right? So that's basically time. So that means achievements of civilization grow according to this differential equation, whereas population grow according to this differential equation. We have two coupled nonlinear differential equations, okay? And as you can see, right-hand side is f times n times f is essentially the same up to some coefficients. That means this equation has integral of motion. Okay, it's very easy. Subtract one equation from another, and you see that the difference of f and n remains constant, okay? So in other words, these equations, it follows from this equation that there is a linear relation between f and n, population n of this f, okay? And once you have this equation, then you simply eliminate f. You say, you use this constant of motion to eliminate f, so your f is equal to some constant plus population, and f is a population growth, you plug it here, and you get this anti-Verhulst equation, the Bose equation that describes population growth. So in other words, I introduced two coupled equations, and then I eliminated one variable, and then I obtained this equation which I showed you in the first slide. It sounds like a pretty trivial exercise, yeah? However, there is one thing here. I want to check, do these equations really correspond to reality? The problem is this, I do have data for population n, but can I measure the strange variable f? And my proposition is the following. You see, growth requires not only knowledge, technology, it all requires energy, right? So the growth requires energy, okay? And what is the source of energy? Well, we know that energy for life on Earth comes from the sun, right? Solar energy comes, plants capture this energy by photosynthesis, and animals eat plants, and humans eat both animals and plants and get this energy. And long story short, for thousands of years, the growth of human population was limited by available live biomass. And live biomass, initially it was like wildlife and then agriculture, so cultivated biomass, that by itself also, agriculture by itself increased population growth, okay? But nevertheless, it was limited by live biomass. And so what happened in 1700 industrial revolutions, human knowledge and science and all that developed to such a stage that humans figured out how to use dead biomass, okay? Biomass accumulated for millions of years, in the form of fossil fuels. As far as I know, only humans figured out how to do this. And once humans figured out how to use fossil fuels, that it suddenly unlocked seemingly unlimited source of energy, okay, in form of fossil fuels. And that's where this crazy, hyperbolic growth started, okay? Because humans now use fossil energy to produce this growth. Okay, and by the way, I heard that for every, I'm not sure, I read this somewhere on the internet, that for every calorie that we eat, we spend 10 calories to produce that food. Okay, so we literally eat fossil fuels. So anyway, so long story short, Then the proposition is to identify this variable f with excessive level of CO2, because it is CO2 which fuels this growth. Okay? And then if that is the case, then we expect, okay, so basically I propose that variable f is linearly related to CO2, but CO2 is linearly related to population, empirically, as I showed before. So what we see is empirical. So we see that basically it shows that empirical relation between CO2 and N confirms the linear relation, the integral of motion, that is expected from these differential equations. So in other words, if I identify f with excessive level of CO2, then yes, data actually confirm these equations of motion. So anyway, long story short, I almost finishing. The proposition is that we have two coupled equations for fossil fuels and population. They mutually enhance each other. So in other words, fossil fuels fuel population growth, and population growth fuels extraction of fossil fuels, and they produce explosive finite time singularity. I would have almost finished here, but there's one more line. These equations, Victor, equations are so simple, so trivial. I was sure that somebody must have written them before. I was just trying to find a reference who wrote and published them before. And 10 days ago, I found the reference. Okay, there was a conference, I attended some conference at School of Business, Department of Finance on this campus. There was finance conference, and somebody was giving a talk and showing exactly the same equations that describe speculative bubbles. Speculative bubbles, okay, like real estate market, for example. Okay, so this was written by Corsi and Sornet. Sornet, I know him very well, Didier Sornet. He is another econophysicist, former physicist, more precisely geophysicist, who then became distinguished professor at business school in ETH Zurich. So 10 years ago, they wrote the same equation to describe speculative bubbles. Roughly speaking, in one word, is something like this. Let's say housing bubble. Price of houses grow. And for that reason, money grows into this house. So N becomes money, amount of money that is invested into, say, for example, housing market, real estate market. Of course, it's proportional, it's related to price of the stock of the housing market. But because more money move into this real estate market, that of course drives the price of housing up. So price increases because money move into it. So you have a self-reinforcing process. More money move into this because prices go up, and prices go up because more money moves in. That produces finite time singularity, and voila, I have 2008 financial crash. Okay, in a nutshell. Of course, that's not the subject of the talk, but what I mean that this equation actually appear in all kind of places. So anyway, so here are my conclusions. So maybe I'll just, time running out, I just quickly show them, but maybe that was too long list. But really the take-home message is two predictions. One prediction is there will be population peak maximum in 2030, 6 years from now, and then population will start to decrease, prediction number one. And there will be peak of annual CO2 emissions in the same year, and then they will start to decrease. Okay, this is my bet. And see you in 6 years. Thank you for your attention.